Hello, my name is Clint Guyman. I get to teach computational tools, Chemical Engineering 263, this fall. I'm excited to do that. And here's the Learning Suite interface and the course website right there. You can click that under Content, and it'll take you to this page. I hope to make multiple videos for class, and those videos you'd be quizzed on, so I'd either make them myself or curate them so you have an opportunity to learn a little bit before class, and hopefully we can spend some time working on homework in class or other class activities. We can work in a small group or get help from the TA or myself during class. Here is that landing page. You can see the syllabus on the Learning Suite. As far as what we'll be learning, we get to learn about Python and Excel, some of those tools to use to help you make engineering calculations, to help you make estimates and make predictions and evaluate processes. There's a large range of experience with Python and other programming languages in the class. So we'll have you'll be assigned to a group, or you'll pick a group to participate in as far as homework, and we'll have several group homeworks. And hopefully that way you get to learn with your classmates and make friends and contacts that should hopefully last throughout your whole life. And additionally, like I say, if you don't have experience programming, that's okay. I'll get up to speed and work together, and you should be just fine. I like to focus on not the hammer per se in terms of talking about computational tools. We all know what a hammer is, to hammer in nails and build things. So we could talk a lot about the hammer itself, but I'd rather work on building a shelf or a table or a building with you. And similarly with programming tools, we could talk a lot about arrays or loops and so on and so forth, variables. And I'd rather spend time building programming projects, and we'll talk about the foundations as well. But we'll spend time working together on actual projects that are meaningful, hopefully, to you for your future homework as a professional student, and then as a professional engineer in the future, that you'll use these tools throughout your career. I've spent, I guess I should have given a quick introduction, but I've spent 15 years as an engineering consultant. And before that I worked at Intel as a process engineer. And I'm just so excited to be here at BYU. So that's a quick intro to some of the things we'll be learning. Spreadsheets and solving numerical and symbolic problems using those computer tools, and writing programming structures, and solving problems with procedural algorithms. Algorithm is just kind of like a recipe to solve a problem. And there's some other items that we'll cover in class as well. But first, these modules we'll go through throughout the course. There's 27 class periods. We'll go through each of these. I wanted to talk about motivation in why you should care to learn about programming and computational tools. Engineers use those computational tools all the time, and they can be very powerful, and there's lots of benefits for thinking critically in terms of learning programming, helping you gain those skills to be an engineer. And I wanted to point out that there's 164 million employed people in the U.S. as of 2022, and only 1 million of those are engineers, and very small fraction of those folks are chemical engineers. So was that 6% of the engineers in the country are chemical engineers. So you're needed. Here's the mean annual wage and the growth, the 10-year expected growth from the Bureau of Labor and Statistics. That's where I got the information for this. It's growing at an 8% rate. 70,000 engineers approximately a year, and 13,000 of those are chemical engineers, and 80 of which, when you graduate, will be you, approximately. You are needed and valued, and there's lots of opportunity to work in a really rewarding career as a chemical engineer. There's lots of problems to solve, as you're aware. Energy rise needs continue to rise throughout the world. There's some links there you can read more about, and we have a number of faculty members that work in the energy sector. You can reach out to them and do some research with them, as well as chemical production. Lots of chemicals being produced, and we need better ways to produce them, and less harmful chemicals, and more recycling, and lots of great things that could happen in terms of helping people throughout the world. Health concerns. There's lots of people that aren't as healthy as they could be, and as a chemical engineer we can help people assess their health and improve that health with whether that's food engineering. There's lots of chemical engineers doing food engineering, and as well as health, once you get sick, tools to assess that health and improve it. There's other topics here that need chemical engineers and the tools that can be used to help solve those problems. And you'll stand on the backs of giants, and you need to be familiar with their successes, and we'll talk about that. And you'll collaborate with others. That's an important skill to have, is be able to talk with and work with others. You'll utilize both computational tools and experimental methods. I love the coupling of theoretical models that you can program on your computer, and the experimental results that you can see with your hands, working with your hands and seeing with your eyes and observing what happens. This intro is to hopefully give you a vision of what the kinds of problems that you will be able to solve at the end of the class. This is not expected that you be able to solve this kind of a problem now, but I'm going to go through this quickly. And first I wanted to talk about flames, and global warming is a real deal, and the climate is changing. There's ample evidence of that. However, there's some misconceptions about how well we've been doing. I don't think we get enough credit sometimes for the improvements we've made through the last 20 plus years. And so here's a plot from the EPA's website. You can click right here and it'll take you there. Here I just wanted to point out is the aggregate emissions. 6 common pollutants. You can look up on that website which ones those are, as well as the CO2 emissions. So this is compared to 1970. So over the years we've decreased those emissions substantially, and our CO2 emissions have gone down, whilst we have increased our population, this blue line here, by 62%. So this is really a great plot and shows the progress we've been making, and a lot of that progress is because of engineers like you. And so there's more progress to be made, but flames aren't going away anytime soon. And here's a example problem talking about the combustion of butane. Here's our butane and oxygen and some nitrogen. This is representing the air, and it's converted to CO2 and water. And we would like to calculate the adiabatic flame temperature. What temperature is that flame? And you can do that with, you learn learn this in 273, as well as your thermal class going forward. But here is a kind of a setup for a Python script or a Python program. And you can download this, open this up in Colab, or download the sheet right here, and you can run this cell. And it has to do with building an object and importing the needed packages. So NumPy is a very popular and common one to do numerical methods. And Matplotlib is our plotting software. And we have integrate and some a param package that's really helpful to make objects. We'll talk about what objects are, what loops are. This is a function. We'll talk about functions and the inputs to those functions. And then calling the object, making from the class, making an object for the different species that are involved. And then using those species to calculate the adiabatic flame temperature. Here's an energy balance showing the balance of enthalpies and how to calculate the enthalpy for each gas species from the heat capacity. And we can also, besides doing it this way, making our own objects, you can use a package called Cantera, and it does a similar thing and has more data associated with it. And it calculates instead of just those two species, but what all the species are in the gas phase. And you can see there's that nitrogen from air, some hydrogen in that flame. This is at the flame temperature. This is 2200 degrees Kelvin, what the species are that exist at that temperature per the thermodynamics of that, each one of those species. So you can also use Cantera to get the species as a function of position, and the flame temperature as a function of position as you move through the flame. We'll talk more about that. Hopefully down here, after we get through some other computational tools. But this is just hopefully representing to you what you can do with Python from a chemical engineering specifically for flames. And here's an experimental setup where we can measure the temperature of the flame and then plot it out and compare it to what we observe theoretically. And you can see it's significantly lower temperature. Why would that be? You can think through that. And so that's video number 1 of our introduction. Hopefully that just gives you a vision of where we hope to go. Don't be overwhelmed with this. We're gonna go through this step by step, and you'll understand it and gain those tools to be a successful engineer. I'm excited for you. God lives and loves us.